Okay, so this is what we've done up to this point is giving us some informative information on the free vibration problem and giving us an idea of making sure we can understand what are the vibration modes that the system would be vibrating. Okay, and what are the what are the associated frequencies. So what you'll see here is there are discrete frequencies, vibration modes that we have for the system. The question is, how many of them do we have? Well, depending on what is the size of this K in M system. So that's the reduced system. That's the one after the pre-sharp displacements have come into play. Otherwise, I do an unconstrained vibration of the thing. That's sort of if things in outer space, not clamped to anything or not constrained in any way. What is the vibration modes? But for a structural system on planet Earth that is in use, there's going to be pre-sharp displacements. And so this is the reduced K and the reduced M of that reduced system. So that's all the free degrees of freedom, that size. And what it tells us is essentially is the number of degrees of freedom that there are. That's the number of vibration modes there are. So if I have a system with, let's say, 10 degrees of freedom, 10 free degrees of freedom after a constrained system, I only have 10 vibration modes. If I have a million, then I have a million vibration modes. And so essentially this is what this tells us. Okay. All right, so that's what we learned from this. So what's important is, what's new is really just this big M. And so to compute it is now a joke. You know what N transpose is. So N transpose N, again, we're going to use Gauss quadrature, and so you can go and figure out for yourself what's the Gauss quadratures, what's required, what is the order of that highest order polynomial of that N transpose N system. So here's a linear one-dimensional bar element example. There's your N1 shape function, your N2 shape function. Here's the mass matrix. There's essentially the description for how to integrate the mass matrix when it's given in the -1,1 domain. So there's already the Jacobian, or the mapping between the dx and the psi walls. Beautiful. And now what we have is, once we've computed this, we essentially have now a way to sort of look at vibration in this 1D case. So there's only left-right kind of how things can move and run, vibrate left and right. Not very exciting, but at least that's really what this description will allow you to do. To say that there's not going to vibrate left and right, each of these degrees of freedom left and right. So how can things then, how does the vibrations look in this kind of system typically? Okay. So this is sort of the 1D bar element. Here's a description if you want to extend this now to trusses. So if you want to place these things in an arbitrary domain in 2 dimensions, I'm really not going to worry about the trusses for now. That's something you've done in MSY 310, 11. It's just generalizing the bar element to a general description. Okay, so I just want to get maybe towards the Q4 elements. You can just say quadrilateral elements. So here is essentially my U field, my nodal displacements for my 2 U fields. Here's my interpolation, my shape functions. We've spoken about this. This is for X, this is for Y. And now I can compute my mass matrix as integrate of N transpose N dj. So in the past it was P transpose dB for the stiffness matrix. Now it's just N transpose N. So that's it. So now I can go and again go and look at what is the highest order polynomial, what is the required number of integration points to integrate this exactly. Okay, and this is the determinant of the Jacobian. And so this is again for if the density is constant. Obviously this density could also be a function of psi and eta if it's a fancy material that you have, or if it changes in some way. But if anything it's a constant, we can pull out of the integral. And that's what that's about. Yes, it's an example for beam elements. I don't want to go too much into that. But this is what I want to get to. It's when we talk about this mass matrices. So this mass matrices that we get out, let's see, do we have an example? So here's an example of a mass matrix, not for the quadrilateral element. This is now an example for a TET element. But what I want you to see is that you can see that this mass matrix has got terms off the diagonal, away from the diagonal. There's lots of terms away. So there's 2 ways and 2 types of mass matrix that gets used in finite element method. The one is essentially the full consistent mass matrix. Okay, so that's the one with all the off diagonal terms of masses everywhere. And then there's this second one, which is essentially that's called the lump mass matrices. And so this is really where with the lump mass matrix, what happens here is all of these rows are off-diagonal stuff are summed and put onto the diagonal, so that this mass matrix only has a diagonal kind of description. It makes the inverse of this mass matrix very cheap to do, to compute, but the implication is that you sort of simplified the mass matrix in some way. And so what you'll see is that the lump mass matrix is used for explicit dynamics, when you have explicit time integration, and the consistent mass matrix is typically used when you have sort of implicit time integration typically. But that's sort of just as a rule of thumb type of thing. But that those are two mass matrices you can go and compute. So the one mass matrix, the two mass matrices are exactly the same. Components, that's the one is just, you have the off-diagonal components, you just have it as you've computed it directly from n transpose n's integral. The lump one, you do some post-processing on that one by summing essentially all the off-diagonal terms and create a diagonal matrix. So that's called essentially the lump mass matrix. Okay, and then we get now towards evaluation of the eigenvalues and eigenvectors. This generalized eigenvalue problem, where there's two matrices involved in this eigenvalue problem. It's not just k u equals lambda u, but now there's an m in front of that. And then here, nicely for the first time in the book, they really nicely talk about the eigenvalues and the properties of eigenvalues, what they mean. Okay, so essentially, if you think about u transpose mu equals 0, that's essentially the I and j are different, and here the I and j's are also different. So essentially what you see is that they are orthogonal with respect to the matrices. This is in this generalized eigenvalue problem. So this is something, once you've computed the eigenvectors, u, I, from 1 to, up until how many degrees of freedom there are, let's say n. If I take one eigenvector and any other eigenvector, so ui and uj, if I pre-post dot it with the M matrix, it will get to 0, and the same with this one. Ui transpose k, uj will go to 0. So what's called is essentially is that these eigenvectors are orthogonal with respect to the mass matrix, and they're orthogonal with respect to the K matrix. It's not that they dot these things directly with each other, I transpose uj j dot product, but I have the mass in between, or I have the stiffness matrix in between. Another thing is that the eigenvectors are normalized, so ui transpose m ui is equal to 1. Okay, that's essentially what this, so they're normalized with respect to sort of this mass matrix, and if I have ui transpose k ui, I recover lambda. So that's just the properties of eigenvectors once you've computed them. Okay, in this generalized format. So anyway, so the generalized eigenvalue problem you can compute in a couple of ways. I'll do that tomorrow, and how we can go about computing these eigenvectors. So we're not going to go do it sort of by hand or this kind of approach. We're going to do it just numerically and make sure we can solve the generalized eigenvalue problem. Okay. So before I